call it chem potpourri because it's not really one group of related topics. It's really just kind of a hodgepodge of things that we throw together at the end of the semester that I think I want to talk about and that you should know about for maybe your future chemistry and or biology class. Okay, so the first topic that we're going to talk about today is the topic of osmosis, all right? So just to define it, osmosis, well, I guess first of all, we need to define something that is important to osmosis, and that is a semi-permeable membrane, okay? So the name kind of gives it away. If you have a semi-permeable membrane, it's a membrane that's semi-permeable. So it's permeable to some substances, but not all. And what you'll see specifically in this context, in this lesson, is that it's permeable to solvent molecules, but not to solute molecules. Okay, and so to define osmosis then, that's where we have the natural movement of solvent molecules across a semi-permeable membrane. Why? Because it wants to equalize the solute concentrations on each side of that membrane. And so the pores in the membrane are sized in a way that the solvent molecules can move through those pores, but the solute molecules are too big. They can't move through the pores in that membrane. Okay, so here's kind of the key thing to remember with regard to osmosis and semi-permeable membranes. The net movement of that solvent is always toward the side with the higher solute concentration, because that's what nature is trying to do. Nature is trying to move solvent molecules to the side with the higher solute concentration because nature is trying to equalize the solute concentration on each side of the membrane. It doesn't like the fact that the concentrations are different on the sides of the membrane. So it moves solvent molecules across the membrane in an effort to equalize those two solute concentrations. Okay, so for example, you have this picture right here, and I believe in your handout you have to complete the picture, so I'll talk a little bit about it while you're drawing. So as you can see on this beaker on the left, this red dashed line represents the semi-permeable membrane, okay? And so the dashes give you an idea about, hey, there's little pores in this membrane, little holes that the solvent can travel through, but the solute cannot. These little purple circles are solute. And so we have a difference in concentration of solute on each side, a high concentration on the right side, a low concentration on the left side. So again, nature doesn't like this difference in concentration, so it's going to do something to try and equalize them. And so since there is a higher concentration of solute molecules over here on the right, and I've got some quote unquote extra solvent on the left, it's going to push the solvent molecules through those pores in the semi-permeable membrane in order to dilute the solute concentration on the right. And so the amazing outcome of that is actually you end up with a different water level, okay, in this beaker. And so in order to equalize the concentration, the solvent molecules from the left side go to the right side, increasing the water level on the right, decreasing the water level on the left. And the outcome would be, if you just let this occur naturally, the outcome would be that you have the same solute concentration after the process of osmosis is done, after it's reached a steady state. Okay, and so it is not very intuitive how this actually occurs. You might be thinking, well, why doesn't the solvent, due to gravity or whatever, why doesn't this just pour back through these little openings and reestablish something like what we see on the left? Well, think of it like this. It's almost like there's a piston or something pushing down on this side. There's this extra pressure. You're going to see in later slides how we define it as an osmotic pressure. So it's almost like there's something extra over here that's kind of pushing the water level down, and therefore it goes up on the other side of the membrane. Okay, so this is an example or an illustration of osmosis, and I got a couple others in the slides coming up here. Okay, so here's a little animation just to show you the same thing. So on the right, these green circles represent solute molecules. And so since there's a difference in concentration between the left and the right side of the semi-permeable membrane, osmosis occurs to try and bring the two solute concentrations to be the same, okay? And of course, it's never going to be achieved in this particular situation because you don't have any solute on the left. So it's just an illustration to make the point of what osmosis is, what is occurring, okay? So the solvent molecules, water in this case, are going to move through the membrane over here to dilute the solute concentration on this side and that results in a difference in water level. Okay, so I think the animation just kind of shows it nicely. But if two pictures aren't good enough, let's go ahead and look at it sort of at the molecular level, all right? So again, these pores, these little openings in that semipermeable membrane are small, and they're so small that the solvent molecules can make it through the pores, but the solute molecules and ions are just too big. So that's why you can have movement of the solvent molecules, but you cannot have movement through the membrane of these other, of the solute ions or molecules. Okay. All right, so as I said before, the way that this is quantified, the way that this is measured is through this thing we call osmotic pressure. And so the definition of osmotic pressure is it's the pressure that must be applied to the solution if you wanted to stop osmosis. Okay, so the pressure that must be applied to the solution to stop osmosis from a sample of pure solvent, okay? All right, so this picture, which you don't have in your handout, but is useful for helping to understand what we mean by osmotic pressure. So on the right here, let's say that I've got pure water in this beaker, but then I also put in this beaker a sample that's 5% sugar, but it's inside this balloon type semi-permeable membrane. So this is like it's kind of like a balloon, but it's a special semi-permeable membrane. And so since we've got pure water on one side of the membrane and a fairly concentrated sugar solution on the inside of the membrane, okay, osmosis is going to occur. And as we showed in the previous slides, the process is going to be that solvent is going to flow through the membrane into the balloon in order to try and dilute the sugar solution on the inside. And so the outcome of that is that the balloon is going to swell as water flows in. Okay, so this water level is going to go down a little bit. It's going to flow into the balloon. But the other outcome of that is it's going to push the diluted solution up through this tube. Okay, and the height of that water column in the tube is how we measure the amount of osmotic pressure. Okay, so that's the way in which osmotic pressure is measured. And it's almost like we would have to apply that amount of pressure represented by the height of this column. We would have to apply that amount of pressure in order to stop osmosis from occurring. Okay, so now you do have this in your handout, but you don't have the osmotic pressure label on it. So you might want to draw that in there. So a couple things about osmotic pressure that we can talk about. First of all, it's symbolized with the capital Greek letter pi, right? Okay, and as we said in the previous slide, that it's based on how tall this column of solution is in this tube. So of course they have a standardized system for measuring it, but that's what it's based on. It's how tall is that column in a tube like this. All right, and so the equation that we can use to calculate it is right here. And so it doesn't really look like it at first glance, but it's very much related to something that we learn about in Chem 1, the ideal gas law, PV equals nRT, because this is a pressure, P, right? Pi, P, and P for pressure of a gas. And so if you take this ideal gas law and you, and if I divided both sides by the volume, right? Divide that side by V, divide that side by V, okay? Well, the number of moles divided by the volume, if that volume is in liters, is a molarity, right? And so that's where this molarity term comes from, okay? So it's like pressure is equal to, we'll talk about what I is in just a second, times the molarity, times the gas law constant R, times the temperature, T. So it's very similar to that ideal gas law that we learned back in Chem 1. All right, so let's just show you what the terms mean in this equation. So the pi is the osmotic pressure. It has units of atmospheres. Okay, M is units of concentration in molarity. Okay, the gas constant, and it's the version of the gas constant with units of liter atmospheres per mole Kelvin. So it's 0.08206. Okay, which remember that's on your equation sheet. And then temperatures again have to be in Kelvin. Okay, so make the conversion. If you're given a temperature in Celsius, you got to make it convert it to Kelvin. All right, and I said I would explain what this I is. The I is something called the Van Hoff factor. VHF stands for Van Hoff factor. And the big thing you guys need to know is that it's 1. It has a value of 1 unless something else is specified. And I'm not going to go over it in depth, but because I don't know whether or not you learned about this in Chem 1, it kind of depends on your instructor and how much, how far you got in the course. It's usually something that's taught, if at all, at the tail end of Chem 1. And so you may not have even got to it in your Chem 1 class. It's a factor, it's a term that takes into account how many particles the solute breaks up into when it's dissolved. So if it's like sodium chloride, NaCl, that breaks apart into 2 particles when it's dissolved. So in that case, I would be equal to 2. And the reason why it's important is because every particle is going to exert some osmotic pressure. So you got to multiply by the factor of the number of particles that the solute breaks apart into. Okay, so let me just do an example type question on osmotic pressure for you. So polyvinyl alcohol, it's a water-soluble polymer with an average molar mass of 28,000. So if you can imagine, you go to the toy store and you see that slime, right, that you can buy, or you can even make it if you have a recipe. But that's basically a solution of polyvinyl alcohol. That toy slime is this polymer that's been dissolved in water. And it is huge. It has a molar mass of on average, about 28,000. And so let's say that you dissolve this much of that in water, 150 mils of it to be exact. And so what you want to calculate then is the osmotic pressure at 27 degrees Celsius. And we're going to, again, assume that the Van Hoff factor is equal to 1. Okay? All right, so remember, this equation is given to you. It's on your equation sheet. You just need to know where to find it, how to use it, when to use it. Okay? So let's just do the calculation here. The first thing I need to do actually is calculate a molarity. Oops. Okay, so I need to calculate a molarity, which of course is moles per liter. And so in this case, it's going to be moles of polyvinyl alcohol per liter. All right, well, I have the mass of the polyvinyl alcohol and I have the molar mass. So that's the first calculation I need to do. I have the 1.844 grams of polyvinyl alcohol. And I know from the molar mass that 1 mole of PVA is equal to, on average, 28,000 grams of PVA. Okay, so grams of PVA over grams of PVA cancel. Right now I have units of moles of PVA, but again, I need molarity, so that's per liter. Well, I'm told that this is in 150 milliliters, which is, that's 0.150 liters. And so I can just put a position holder there in the numerator, 1, and I can just divide my number of moles by 0.150 liters, and that will get me a molarity of this, the concentration of this polymer. So let me just do that calculation real quick. So we got 1.844 divided by 28,000, enter. And I'm also going to divide that by 0.15 liters. And I get I'll say 4.39 times 10 to the minus 1, 2, 3, 4. So 4.39 times 10 to the minus 4 molar. All right. So that's my molarity term right there. So I can just calculate the osmotic pressure. I is equal to 1. We're told that. The molarity is 4.39 times 10 to the minus 4. Okay. And, well, scratch that. Let me write out the units there. So moles per liter. And the reason why is because I'm going to use R, 0.08206, and that's liter atmospheres per mole Kelvin. Okay, and that I wrote that out so that you can see how the units cancel. Moles over moles cancel, liters over liters cancel. And so I'm also going to multiply by the temperature. So the temperature is 27. So if I add 273 to that, that is 300, if I'm not mistaken. Okay, sorry for the chicken scratch handwriting there. So 300 Kelvin. So now my units of Kelvin cancel and you get an atmospheres, or you get an answer in the unit of atmospheres, which is what you're looking for. Okay. All right. So I will erase that and let PowerPoint present it again, all nice and pretty. Okay. So I calculate the number of moles. Then I calculate the molarity by just dividing the number of moles by the volume in liters. Okay. And 300 Kelvin. Okay. And assuming I had all the correct numbers the first time, then that comes out to be 0.011 atmospheres, which if you wanted to convert that into torr or millimeters mercury would be 8.2, the equivalent. All right, so let me do another type of example problem that involves osmotic pressure, and that is calculating the molar mass from an osmotic pressure. Okay, now this is actually kind of a real world type problem because in biochemistry, molecular biology, when someone discovers what they think is a new protein, a lot of times what they will use to determine the molar mass of that protein is this type of osmotic pressure analysis, because the techniques that we use to measure osmotic pressure are so accurate, that, so precise and accurate that it just works really well to get a good measure of the molar mass. So let me just kind of demonstrate how that's done. So for example, lysozyme is an enzyme that breaks bacterial cell walls. Let's say that we have a solution containing 0.150 grams of this enzyme, and it's in 210 milliliters of solution, and it gives you an osmotic pressure of 0.953 torr at 25 degrees Celsius. What is the molar mass of this substance? And again, we're told that the Van Hoff factor is equal to 1. Okay, so a couple things we need to do. First of all, let's convert this torr into atmospheres, because we know that that's going to be the units that we need for the calculation. And also, we need to add 273 to this. So that is familiar enough. That's 298 K. Okay, well, if that 0.953 torr, we need to change that into atmospheres. So let's see, if I divide 0.953 by 760 torr, because 1 atmosphere is 760 torr, then I get 0.00125 atmospheres. So this is equal to 0.00125 atmospheres. Okay, all right. So those are the two numbers that we're going to actually use in the calculation. So So once again, remember that this equation is on your equation sheet. The osmotic pressure is equal to the Van Hoff factor times the molarity times R times T. Okay. So the other thing that we can do, and this is the important part, is that remember that molarity is moles per liter, okay? And so the first thing I need to do is kind of substitute in that relationship. This is moles per liter, right? And the reason why is because what I'm going to solve for really, first of all, is moles. And then once I know the number of moles by using this equation, rearranging and solving for moles from this equation, I also know the mass. So remember that a molar mass is just, it has units of grams per mole. So once I find the number of moles with this equation, I divide this mass by that number of moles, and I have units of grams per mole, which means I have the molar mass. Okay, so let's start plugging in some numbers here. So the osmotic pressure, we are told, is 0.00125 atmospheres. Okay, and that equals 1. The Van Hoff factor is 1. And then that's times moles per liter. Well, okay, so I'm told the volume is 210 milliliters. So that's 0.210 liters. Okay, and then R is 0.08206 liter, chicken scratch again, sorry, liter atmospheres per mole Kelvin. And then I multiply that times the 298 Kelvin. Okay, so Kelvin cancels. Well, what I need to do is just rearrange and solve for this. Okay, so the number of moles, then if I divide, let's see, if I move everything else around the moles over to this other side by multiplying both sides by the 0.210, so that's 0.210 liters times 0.00125 atmospheres. Okay, and then I also divide by R, so divide by 0.08206, and that has units of liter atmospheres per mole Kelvin. Okay, and then I also divide both sides by the 298 Kelvin. Okay, so now units of Kelvin cancel, units of atmospheres cancel, units of liters cancel, and I have units of 1 over moles, which when I actually calculate the answer will give me some answer in units of moles. Okay, and so then once I get that, what I'm going to do is I'm going to divide 0.150 grams of this by that number, this number of moles. Okay, which will give me some other answer in units of grams per mole, which is, that's the same thing as the molar mass, and that's what I'm looking for. Okay, all right, so once again, just to make it look nice and pretty, I will erase all that, and we'll let PowerPoint take over. Okay, so again, using this equation, calculating the number of, calculating the osmotic pressure in units of atmospheres, generating molarity, getting number of moles. Okay, so this is the number of moles of the enzyme, and so then this the mass of the enzyme divided by the number of moles of the enzyme gives you the molar mass, which in this case is 13,900. And remember, that's a reasonable number because enzymes are proteins, and proteins are very large molecules, and therefore they're going to have very large molar mass. So something else we want to talk about with regard to osmotic pressure is the sort of the medical terminology. Okay, so you may have heard these before, or in some other class or something similar anyway. But if we say a solution is hypertonic, if we say a kid is acting hyper, it's got too much energy, right? Well, hypertonic, that means it's like got too much dissolved in, there's too much solute dissolved in the water when compared to a living cell. So the way in which that would be expressed in terms of osmotic pressure is that the osmotic pressure of the solution is greater than the osmotic pressure inside of a cell. And so the consequence of that, the outcome is that you've got water in the cell. It's going to rush out of the cell and into the surrounding solution in order to try and dilute the exterior solution. Okay, so there's going to be a net flow of water actually out of the cell, which obviously is not healthy for the cell. Okay, so the sweet spot where you want it to be is the term isotonic, right? And that's where the two osmotic pressures are equal. So the osmotic pressure of the solution is equal to that of the cell. And so there's just no net movement in and out of the cell. So the net movement in and out of the cell is zero. There's going to be water moving through the cell membrane, out of the cell, back into the cell. That's just natural. But the net movement overall, there's not going to be a gain or loss of the amount of water in the cell. Okay, so we've had hypertonic, isotonic, and now the last one is hypotonic, and that's just the opposite of how we started. And that's where the exterior solution has an osmotic pressure that's less than the osmotic pressure of the cell. So this would be like pure water. This is why you can't grow cells, bacteria or cells in pure water, because pure water has no solute dissolved in it. And so what's going to result is that you're going to have a net flow of water into the cell to try and dilute all of those solutes that are dissolved in the cytoplasm, right? And so a picture of that is on your handout as well. So if your exterior solution is hypertonic, then all your cells die because the water flows out of the cells and into the exterior solution. And in a futile attempt to try and dilute the solute concentration outside the cell. Okay. Isotonic is where they're nice and happy. And then hypotonic is just as bad as hypertonic, because what happens is the water outside the cells flow into the cells and cause them to burst, right? And so that's why anytime that somebody receives anything intravenously, a medicine or whatever, it has to be in a isotonic solution, which is typically a sterilized 0.9 sodium chloride or something along those lines. But the idea is that it can't just be pure water. It has to be isotonic with cells. Otherwise, it just kills any cells it comes in contact with. And so, for example, the other thing I'll say is that, when you experience your skin getting all pruny, like when you take a bath, or if you swim in seawater or really chlorinated water, why your skin gets all pruny is because that's a hypertonic situation. The water rushes out of your cells into the pool water or the seawater or the soapy water in an effort, or just through the process of osmosis, and that's why your fingers get all pruny. Okay. All right, so one other application to talk about quickly is reverse osmosis, because this is used a lot these days to purify water. A lot of countries rely on this. Like I know that Israel, for example, they don't have wells, well, not very many. They don't have springs and wells, things like that. A lot of their potable water that they use is through desalination. And so we said that osmotic pressure is like this ghost pressure on one side of a semi-permeable membrane. And so there's, the laws of physics or whatever says, well, what if we just exerted a little bit more than that pressure? Then we could use this and exploit this phenomenon to actually purify water. And you can see it in this picture. So if the seawater is coming in, and the osmotic pressure would be, well, over here we have fresh water. And so let me turn my laser pointer back on. So if we have seawater on this side and fresh water on this side, there would be this natural tendency of the fresh water to flow through the membrane over here. And remember that the term osmotic pressure says, well, what is the pressure we would have to apply to keep that from happening? So if this piston applied the same pressure as the osmotic pressure, nothing would happen. But if we apply with this piston just a little bit more pressure than the osmotic pressure, then we can actually use this process to purify that seawater. Because what's going to happen is it's going to push pure water through this semi-permeable membrane if we apply a pressure that's just anything more than the osmotic pressure. okay? Because the solute, all the salts stay on this side, but the pure water flows through this membrane to the other side, okay? So that's what we mean by reverse osmosis. An external pressure is exerted to counteract and overcome the natural osmotic pressure, forcing water molecules through the membrane, thereby producing purified water. Okay, and this again is just an animation of how that all works. So over here is like the seawater, all the yellow circles are the solute, and so they just get kind of concentrated and then kind of pumped away as a really concentrated briny solution. And over here, it has it's never perfect, so that's why they have some little and a few yellow circles. But in general, as we apply this pressure greater than the osmotic pressure, it concentrates the salt and pushes the pure water through the membrane. Okay. All right, so since we got the chat box, hopefully you guys can see your chat box. I want you to think about this question, and this will be it for today. We'll call it a day. So let's say that we have this situation right here. We have a semi-permeable membrane in this container, and on one side we've got water with red food coloring, and on the other side we have pure water. And so just to show me that you understand what this is all about, you have several choices here about things that could happen. So consider them, and I want you to submit in the chat box what you think, which answer you think is best for what's going to happen here with regard to osmosis. And I'll shut up for a minute and let you submit your answers. So remember that the solute, the reason why the water is red is because something is dissolved in it that's making it red. Okay, so now I'll just go ahead and talk about it. I'll show you the answer, because some people are just getting the exact wrong answer. So let me explain why.
Ding, ding, ding. What do we have for Johnny?
Why I is the correct answer, okay? Because solute molecules cannot cross this membrane. Only the solvent can cross the membrane. But there's going to be some movement in order to try and bring the two concentrations to be the same. And so this pure water side, that's going to push water through from side A to side B, okay? So that means that the side A's water level will rise, okay, and the side B's water level will go down. So G, so D and G, and side A is going to become less red, less intensely red, because as this pure water pushes through, it just kind of dilutes the red food coloring on this side, and so it becomes less red at a higher level. And this side B becomes a lower water level, okay? So if you need more time to kind of think about it, it is not super intuitive for most people, but that's an important kind of concept I want you to get from this lesson, okay? All right, so we'll stop there. Kind of appropriate for a Zoom lesson, I guess. So the homework questions from the Unit 7 homework assignment that you can do based on this lesson are numbers 1 through 3. So you should be able to do questions 1 and 2 in the extra practice assignment. Also, since we're getting closer and closer to the end, I just want to sound like a broken record and remind everybody about the review assignment and then some good tutorial videos on this topic.